default firewall. Then we will talk about how to develop Shellcode today. So this is the fourth defense we talk about to defeat Stack Overflow. But this approach doesn't only defeat Stack Overflow. It also defeats other attacks. The full name of this is Address Space Layout Randomization. A little bit of history about this approach. Like I said, it's not supported well in embedded devices at this point, mainly because those embedded devices, they do not have MMU, memory management unit. Their address space is very small, it's not virtualized. However, all our other systems, your mobile phone, your laptop, your tablet, they have MMU. The address space is virtualized. We have enough entropy to do something. So 23 years ago, Linux had this patch to have this address space layout randomization feature. Then OpenBSD had that. Linux added the user space support for that back in 2005. The Windows, iOS, Android, all of those systems have this feature. Linux kernel also added this 10 years ago. The idea of this is very simple. We are trying to slow down the attackers. So let's say you put your shellcode into the address space. Even if you put a huge knob stack there, you still need to get it relatively where your shellcode is, right? The idea to defeat those kind of attack is to randomize everything in the address space. So every time you run the program, the libraries, the stack, everything else, they are at a different address. They're not at the same address. And this is supported at the compiler level first. The compiler level, we need to compile programs using a flag called PIE, Position Independent Executable. So sometimes it's called a Position Independent Code, which means some instructions, those pieces of instructions, they can execute anywhere. Doesn't really matter where you put it. Okay, so this is address space you saw at the very first class. This is at a 32-bit machine for Linux. Usually the address space looks like this. At the very low memory locations, addresses, we have the code itself. Then we have the data segment, we have the BSS segment, which is uninitialized variables. And we will initialize all of them to 0. Then there is heap, there is system libraries, also C libraries. Then go higher, we will have stack. Then the higher 1 GB, we reserve that for kernel space. So that's the address space. And looks like it's fixed, right? So all the examples we have seen so far, like this one. This overflow return 7. Does it print out any address? Oh, this one doesn't really print out any address. Which example let me just use another example. Just use ASLR 32. So this program prints out the address of many things in this program. Let's take a look later. Okay, so the traditional address space looks like this. This is static. The text is always placed at a fixed location. All other sections, they are placed at a fixed location. Even if there are shared libraries, they are placed different processes. They share libraries. So the hardware level, there is only one copy of that library in the DRAM. However, at the each process, their point of view, they have their own copy. But even that, they are at fixed addresses. So the address-space layout randomization idea is to let's randomize the address of everything. The text, the code, doesn't have to be at the beginning of the address space. The heap doesn't have to be there. The stack can also go other places. Every time we execute the program, we choose a random address to place it. So this is a first example. We are going to say this is address space layout randomization example 1, and the main function just print out the address of everything here. We have 3 global variables, k, I, also a pointer p. Then we have 3 functions, and, sub, compute. Each function, they have some local variables. The main function just print out their address. First, we print out the C library function address, the address of printf, the address of memory copy, the address of, and also print out the distance between printf and memory copy. Also, we print out the system's address and the distance. Then the module functions, which is the functions we, the developers, developed. The main function address, add functions address, the distance, and also global variables address. We just print them out. So if we go to here, go to our platform, right now we disabled ASLR. For all the challenges you have done so far to make it easier, we disable ASLR. But for all our modern systems, we enable that. So you can see the printf, the C library function is at this address, F7, E2, blah, blah. So no matter, let's run this program again. You see, they're still at the same address. Let's say, it's hard to compare, right? Okay, here. So on top, that's our first run of the program. Here is the second run of the program, but you can see they have the same address, F7, E2, 33, 40, F7, F2, 1D0, okay? They're the same address. So now let's take a 10 minutes break, and during that 10 minutes, I will ask the TA to enable ASLR. Then we revisit this one again, 10 minutes later. We come back 6:05. Okay, let's go back to the ASLR 1 function. So I run, now the TA has enabled ASLR on our platform. And you can see I have two windows run two copies of the same program. But the address of those functions are not the same anymore. The left-hand side, we had printf at 1340, and the middle will be E1 something. However, this one, the address will be D873, but you can see the last 3 bytes, they are the same. No, well, this is half byte. The last 3 digits, they are the same. This one you can see the last 3 digits are the same, middle are different, the top 2 looks like the same, right? However, the distance is not changed. The distance between printf and memory is 1640. The new version is also 1640, right? So, which means this Linux implementation of ASLR, the granularity is not at the function level, right? It's a region. The code region itself, the whole code region is placed at different locations. But the relative address between what inside that code region, they do not change. The module functions, you can see that their address also changed. Here is 58A2, here is 5F, line 2. So if we run this again, you can see it will be it will also be a different address. Okay. So that is how ASLR works in Linux, and this is deployed in Windows, Linux, and all other systems. How this is implemented: whenever a new process is created using the system called execve, the kernel needed to prepare the memory for that new process, and at that time, kernel will randomize the address every time. However, you can see the entropy, at least for the 32-bit version, the entropy is not very high. Only the middle, maybe 3-4 digits are changed. So 4 digits are most 12 bits, right? So that's 1024. 10 bits is 1024 possibilities. So not very high, still can be brute forced. So if we check the symbols of them, you can say, that's why for some of programs, if you check the symbols, use NM, you will say their address, those symbols, their address looks like very small. That's because that's just an offset. The base address is randomized when the program executes. So this is just an offset. It's not really the runtime address. So the overhead for PIE actually is not very big. To run programs 32-bit, the overhead is a little bit higher, still smaller than 3%. You see a lot of functions like this, __86.get pc thunk, then ax, bx, something like that. So that function is trying to get the address of its, basically that instruction's runtime address. Because when you compile that, it's not static. The address is not static anymore. The address is only determined at runtime. So that piece of code is trying to figure out where I am at. For 64-bit version, because the instruction set is more powerful, we don't even need that function anymore. For example, the data can be placed at a fixed relative address to the current code. Then when we move them together. So their relative address doesn't change. Then we can just use RIP plus something to get the address of data. However, 32-bit, we don't have instructions like that. To disable and enable ASLR on Ubuntu, those are basically the commands you can use. Our platform runs Ubuntu. However, you don't have the privilege to do so because you are in a container. So the TA just did something like this to enable ASLR. We already saw this. When we compare that, they have a different address. 64-bit, the entropy will be higher, much higher actually, as you can see here. Probably will be, I feel the middle 6 digit, maybe the 6, 7 digit, that give us 20 bits something of entropy, which is much higher. However, like all other approaches, this is not perfect. There are many ways to bypass ASLR. First one is address leakage. Some vulnerabilities allow attackers to obtain the address required for attack to bypass this. And also relative address, like we said. You see the implementation here. This implementation, the code section, the whole section is moved around. Not different functions are moved around. So the entropy is enough. It's not enough. If you know the relative address of two functions, no matter where you move the whole thing, their relative address do not change. Also, implementation weakness. Some vulnerabilities allow attackers to guess address due to low entropy. Also, there could be side channel attacks to help us to guess the address. So here we have the second example, and now we already enabled ASLR, but we are going to attack this. So actually most of the challenges you did so far, even if we enable ASLR, you will be able to get the flag. It's just take a little bit longer. Okay, so a very simple program, main function, take input from command line argument, then call the valfoo function. The valfoo function first print out where it is, where valfoo is. Then there is a buffer, then there is a memory copy. So that's a classic buffer overflow we are familiar with. Then in this address space, there is a print secret function, and the idea is to return to the print secret function. We do not know the address of the difference between this one and previous attack is we don't know the address of print secret. Right? So let's take a look. Level 2. Okay, here. So every time we run this program, you can say valfoo has a different address. And every other functions in the address space, like print secret, also have a different address. Valfoo, this one has 5657. Here we have 5664, right? So the middle 3 digits are changed. And most 12 bits are changed. So how do we hack this one? Any idea? If we look at the disassembly, you can say valfoo is at, this is offset compared to the whole code section, it's at 1408. And the valfoo is called by the main function. A main function is at 13 A line. Then where is print secret? Print secret is at 13 8D. And the particular function we are looking at is actually, where is core valfoo? Calling valfoo is here. Okay. Calling valfoo is at 13 F6. Okay. So how do we hack this one? We want to return to print secret, but we don't know its runtime address. We only know the offset here. From those address, what kind of pattern you see here? So the main function will call val foo, right, here. So when val foo returns, it will return to where? This one, 13 FB, right? So the return address on stack will be what? First of all, how big is the return address on stack? 4 bytes. Then the 4 bytes will be the 3 bytes, we don't really know, right? The runtime address, but the last byte will be what? FB, right? Then where is print secret? Where it have the same first 3 bytes, the most significant 3 bytes will be the same? It actually will be the same, right? Because they are so close to each other. They are in the same page, actually. So print secret is at D8. We are going to return to FB. So to overflow this one, to capture the flag of this one, it's actually very simple. We do not overwrite the most significant 3 bytes. We only override the last byte, even if we don't know the value of the first 3 bytes. We don't need to know that. We don't touch that. We don't change that. Does that make sense? Okay, so let's say the buffer is at, so this one is a memory copy. So the buffer is at EBP plus 8, right? Here, EBP, no. EBP minus 10, sorry. EBP minus 10, that's 16 bytes, then 4 bytes of garbage, 20 bytes, then just the 1 byte change to 8D. That's it. 8D or 91, either way. Yeah, that's it. So that's very simple. Let's see if it works. We need 20 bytes of garbage, then 1 byte D8, oh, that's 391, I guess. 32-bit doesn't really matter, D8. 8D or D8. $8D. Okay, that's it. Let's see. Yeah. It works. Even though the address is randomized, we didn't change it. The program already put the correct address for us. So if we run this program again, you can say val foo, it will be at a different address. Right? It's changing. The address is changing. However, we didn't change that. So even though looks like this is a very smart defense, there are loopholes in the program, in the system. We can bypass this defense. So that's basically ASLR. ASLR, like I said, is still a very hot topic for research. This is a paper published 7 years ago. This one proposed to re-randomize the address space when the program executes. Like I said, the current program, even 7 years after this paper was published, how it works is when the program calls execve, the kernel will randomize it. Even if the program calls a fork, It will not re-randomize it. Same as the stack arrays. If the program runs there forever, like a web server, then it doesn't really utilize this address space layout randomization. It was only randomized at the beginning. The kernel, the same thing. The kernel's address space is only randomized when it boots. But how often do you reboot your computer now? Not very often, right? So this paper proposed to re-randomize the address space at some point when the program, after the program execute for 10 minutes, for an hour, something like that. But however, this is a very difficult problem. As you can imagine, when the program executes, for complicated programs, there are so many pointers point to each other. There are so many addresses in the address space. And when you randomize things, you have to fix all the pointers, which is a very difficult problem. So this was published 7 years ago. I would not say it's very practical because sometimes it could be, there's maybe some errors. So the second defense approach we are talking about is called the secure computing mode, Seccomp. This is also deployed on our Linux systems. This is basically a firewall. So if you took the computer security class, you know firewall, usually when we say firewall, we mean network-based firewall. Means some packages are allowed to enter your network, some packages are not allowed, right? Then at the system core level, this allows developers to write rules, complex rules, to allow certain system calls and disallow certain system calls. And the rules are complicated. If you are you want to learn more, you can go here. I will just show you some simple examples. So this was first developed in 2005 for those super computers merged into the Linux kernel at the same year. Also, Android use this BPF filter. Actually, it's BPF based. BPF is another kernel, interesting kernel feature. This is quite new. Still a lot of research on BPF. So here is one example of Seccomp. The program is very simple. First of all, let's ignore this what inside this macro. This program, it's just a main function, and the main function just execute bin cat, then cat the flag. Basically, read the flag, right? That's simple. Let's take a look at this program. This one, Seccomp allow. The code is like this. Just execute a new program and cat the flag. So we should be able to get the flag by calling this. Okay? So simple, like that. And the other version we have here is we define this sandbox. Then in this sandbox, we first get this Seccomp context. Then we initialize this. Then we add a rule. The rule here is, this is basically the rule. The rule is if the program execute the exe CVE system call, then we are going to kill this program. Okay? So here means you execute this system call, then we are going to kill this program. That's it. Okay? So when this part is compiled, to enable those first. So here you have the code to disable that system call. You only need to inject code to enable those things first. Then make the system call, right? So all of those, they're not perfect. So this is another difference I want to talk about. Okay, so the second half of today's class, we are going to develop some shellcode. So far, you have been using shellcode. You have not written your own shellcode. So today, you are going to write a little bit shellcode yourself. If you want to learn more about how to write shellcode, actually, there are many books. I learned a lot from this book. It's kind of old, probably already 15 years old. They have shellcode for many different systems, Linux, Windows, BSD, different things. So today we will talk about long-zero shellcode, not printable shellcode, alpha-numeric shellcode, English shellcode, and recently we found a paper about the DNA shellcode. So we'll talk about that. So this is the shellcode you have been using, you are familiar with. They are basically just the bytes. They are just machine instructions. We already discussed what they mean. So if you don't record, go back to previous videos. When I started my PhD in 2009, and I find this paper, which is English shellcode, and I found it very, very interesting. So the shellcode we had before, you see that most of those characters, they're not printable characters, right? They're machine code. They're not printable characters. So back in 2009, those researchers, they find out that you can actually not make the shellcode just ASCII characters, but make them look like reasonable English. So here's an example. So the English-wise, it's this paragraph, right? There is a major center of economic activity such as Star Trek. Maybe it doesn't make sense as English, but still, at first glance, it looks like English, right? But this, you interpret this as ASCII character, it reads like English. However, if you interpret this as x86 code, it will be something like this. It will push ESP, push a value, multiply something, and they are meaningful instructions. Not only they are meaningful instructions, they are instructions can exploit your program's vulnerability. They are the shellcode, right? So if someone is chatting with you using, I don't know what you guys use now, WhatsApp? What do you guys use for instant messaging now? Okay, something like that. Or even just short message, right? Someone is texting you with English. They could be texting you shellcode, exploiting the vulnerability of the program that is receiving those messages. Okay? So something even more fancy is this DNA shellcode. This paper was published 6 years ago, published by researchers at UW. This professor, Yushi, he did many very cool projects. He was among the first to hack cars. He was the first to show us we can hack DNA sequencers. He also was the very first to hack AR, VR devices, I believe. They have many interesting projects. So in this paper, they showed that we can create DNA sequences that to exploit the vulnerabilities in your DNA sequencing software. So DNA sequencing software, they take input like this. DNA analysis software take input like this. So you can see here, they are basically CTAGs, and they are associated with the possibility of the each DNA character here. and they are stored in something called a fast queue. Then this one will be read as input, read into your DNA analysis software, and the DNA analysis software may have a bug, may have a buffer overflow, like what we saw. Then, to inject your shellcode, you only need to encode your shellcode into GCAT, nothing else. Okay? You cannot use non-printable characters. You cannot use other ASCII characters. You can only use GCAT. Only use those characters, you can actually create shellcode. Just use those 4 characters, you can create Turing-complete instructions. That's amazing, right? Then they develop some shellcode, encode that into CTAG, then they synthesize that into real DNA, okay, in this small tube. Then use the DNA sequencer to read that. The DNA sequencer reads something like this, and this is input into the software to analyze the DNA, which has a vulnerability. Then that one is hacked, and you get a reverse share back for that. So very interesting work. If you want to read more, just download the paper. So this actually, I think this can inspire us to do a lot of research that attack the cyberspace from the physical space, like LiDARs. So all the autonomous cars, they use LiDARs, and the LiDAR basically, they have lasers, reflected lasers. Eventually, that will be digitalized into some data. That data will be analyzed by the planning module of autonomous driving system, right? If the planning module has some software variability, so which means if you shoot some carefully crafted laser to the LiDAR system, you will be able to crack the software of autonomous cars, right? That's one example I have been thinking recently. All other cyber-physical systems, I think, will have the same problems. The input from the physical world eventually change the digital world, and we can trigger software vulnerabilities we talk in this class. Okay, so how do you develop shellcode? In this class, we just use a very simple template. You just use .global start. So this is your assembly file. You just need to define one function, which is a start. This is not even a function, a label, start. Then you have a save start. Then you just put your instruction here. Then you can start code your shellcode. Then after that, how do you compile that? Let's say your shellcode file name is shellcode.s. Assembly code there. You use GCC, 32-bit version. You just compile it to the 32-bit version. You don't need any libc library. So you give the option no std lib, compile it as a static. Then the output will be shellcode. So this is the same. You compile any other C program or assembly. So which means the output of this is actually an ELF file. An ELF file has the ELF headers, have a lot of meta information you don't really need. So the binary utility, they have another tool called obj copy. And for this one, we can copy the raw instructions from the ELF file. This is the ELF file, this is the input, and we want to dump the .text section. Then you can get those pure machine instructions from your shellcode. Because you didn't use standard library, so there is no like those C, libc, elite functions. Do not have those things. The 64-bit version, almost the same thing. It's just you do not compile with 32. And on our server platform, we have several tester challenges for you. It's, let's say, For example, this one is tester long 0, which means your shellcode cannot have any 0 characters there. Okay, no 0. That's it. So the shellcode I give you guys on the slides, they do not have zeros, so they can pass this kind of test. So how those testers were implemented? Very easy. Each tester function is like this. It's a main function. Then I create a new page in that program, and then I just read whatever from the std_in, which is supposed to be your shellcode. I read that to that page, which means your shellcode can as big as 4 kilobytes. Obviously, most of the shellcode are just 100 bytes or even smaller, but we read that. Then we just call that. We just give control to that. So whatever your input is, we execute that. And your job is to get the flag, right? Different testers, we will add a little bit constraints there. For example, this no 0 tester, we are going to use string copy instead of, so after the read, we are going to do a string copy. So the string copy will end at 0. If your shellcode has a 0, we will not copy the full of your shellcode. We will copy until there is a 0. Or there is an ASCII shellcode. In this shellcode, you are only allowed to use characters between 0 to 128. I do make 2 exceptions. You can use CD and 80. That's for the int 80 system call. If we do not allow this, this will be much, much more difficult. You need to make your shellcode. So this corresponds to the int 80 instruction. Okay, it's very difficult to replace that instruction. Almost impossible. It's impossible to replace that instruction. Other instruction you have seen that. If you want to set a register as 0, there are many ways we can do that, right? We can set that register to number 1 first, then we decrement that, then it's 0. We can do an exclusive OR, it will be 0. We can put, there are many other ways, right? However, the int 80 instruction is very hard to replace because that's a system call instruction. And you need a system call. You need to do execve, you need to change the program's set UID, right? So because of that, I allow you to use CD and 80. Without this, your shellcode has to be self-modifying, okay? Which means after your shellcode is read into the memory, your shellcode need to modify itself to insert CD and 80 there as its own instruction, which will be much more difficult. Okay, so this one is a tester ASCII one. Your shellcode can only have ASCII characters. Then those for 64-bit and 32-bit. So the homework, and you can start now, of this week is to develop a shellcode. Let's say, where's the homework? So the homework will be due next Tuesday, because tomorrow you have another homework due. So after today's class, we will disable ASLR again for those who haven't finished homework 7. Tomorrow night, we will enable ASLR again so you can finish homework 8, start working on homework late. The first several homework are actually very simple. The first 4 are very simple. You do not need to get the flag, basically. This one you need to get the flag, but you only need to override 1 byte. Then the 5th homework is to develop a 32-bit ASCII shellcode, which you can start now. What the idea is, you already have a working shellcode, like this one. This is a working shellcode, right? Those are valid shellcode, then you don't really need the last part because remember that's the exit 0 part. So there are probably 20 instruction here. Okay, so for each instruction, you can say the raw byte, whether they are an ASCII character. Some of them are not. For example, this one, B0. This is not an ASCII character, which means you need to change this instruction. You still want to move number 5 to the register AL. However, you cannot use this instruction. You need to find other instructions which is equivalent to this one. However, their number is small, right? It's smaller than 7F. Oh, even this instruction you cannot use anymore because there is a C0, right? For those instructions, you don't need to change because we do allow that. You say CD80, we do allow that. Okay. To make it easier, you don't need to do this part. Okay. Then after you are done, you can pass that to the tester ASCII one. If it passes, get the flag, then that's basically the homework. So we do have a bonus question this week, 20 points bonus. The bonus one is not necessarily harder than the previous one, actually. Maybe easier, but I just want to give you guys some bonus. This one, you need to develop a 64-bit version long-zero shellcode. I guess the version I gave you guys before, did I have the version I gave you guys before has 0? Oh, it doesn't have 0. Okay. Looks like this one may work. Okay. Okay, as long as if this one works, you don't need to change anything, and you get the flag, then everyone can get the bonus points. Yeah, looks like there's no 0. Do you see a 0 here? I don't see a 0. Yeah. Oh, okay. So this one actually works. Okay. I should change this to ASCII, but whatever. I already set non-zero, then non-zero. Okay. Okay, you guys can start now. I try to walk around to give you some ideas how to. I hope you work on this question, so I can help you. Yeah, this one. So where do we start with this one, right? So here you can say we already have some. This is 64-bit. Let's do the 32-bit. Let's do the one without non-share shellcode. Yeah, this one is good. So you just copy this one. Here. Copy this one. And you don't need this part, right? I guess we can ask ChatGPT to remove this part, I guess. Let's try. I don't have an account here at ChatGPT. Okay, let me on my own computer, and if I get that, I will send you that file. I suggest you to use the long share code one because this one's easier. Fewer instructions than this one, I think. I think this one is slightly more. This one should be, this one I think should be, this one should be easier, yeah.